What is up, guys? This is Physics 2212 Lab 5 Magnetic Braking with Faraday. Here's a table of contents. Alright, starting it off with some key concepts. Force on the current carrying wire, also known as the Lorentz force, is equal to ILB sine theta, or IL cross B, and we're going to consider our specific case where we're going to drop a magnet in a tube of aluminum foil. So our L in this scenario would be the circumference of the foil, which is 2 pi r. And Ohm's law, V equals, or voltage is equal to current times resistance. We can also rearrange that, which was going to be more helpful in this lab, for I is equal to V over R. And next is Faraday's law of electromagnetic induction. It describes how a changing magnetic flux induces an EMF in a circuit, which we can see in this formula right here. And the negative sign reflects Lenz's law, which states that the induced EMF opposes the change in flux. And this is our formula for flux, BA cosine theta. And flux depends on the field strength, loop area, and orientation, as we can see here. And now for my procedure. Here is me dropping the magnet in the tube. Now, as you can see, as it falls, you can see how much it's slowing down. So as this magnet has a velocity downwards, it's inducing a current in these coils, and that current in turn provides a magnetic field in the opposite direction of its descent, which slows it down, as you can see here. And the average of these ended up being 0.93 seconds in the tube. And for my computational model, I'm designing this exact scenario. So we have some constants here, the exact dimensions of my tube, some numerical parameters just for the calculations, and this is for the bar magnet initial conditions, and this is where we actually start making some calculations. We're calculating the dipole field of our specific bar magnet, and then we're calculating the change in flux in this function right here. And then we're using those functions to pretty much iterate as the magnet falls through the tube. It's going to calculate those two, and it's going to, we have some updates right here. And at the end, we're going to use those forces to update its velocity and position. And as we can see, it models just that. As it goes through the tube, it is slowing down, and I could speed up the rate. But yeah, as you can see, it goes through the tube. It is slowed down because that was 0.7 seconds, but it makes a good point. And next, we have what happens to the dynamics of the system when you flip the magnet around. It pretty much does the same exact thing, except the polarity of the magnet reverses. So an induced current will be of the opposite direction. And how does the total time in the tube compare to the real experiment? In the real experiment, obviously we got slower times. This could be from the friction on the sides of the tube, error in calculating the time. There's a lot of errors that can go into that. And what if the resistivity of the conductor were reduced as close to zero as possible? So this would essentially make the induced current way higher, because if we remember our formula, I equals V over R. As R goes to zero, that means there's nothing reducing your current. So a higher current will mean a greater induced magnetic field pushing in the opposite direction. And what if holes or slots were cut into the tube? If holes or slots were cut into the tube, this would prevent current from flowing all the way. So the effect we just saw would pretty much be nullified depending on how big the cuts are. And that's it. Thank you for watching.